Okay, continuing with the method of Frobenius and the Bessel function of the first kind. Okay, let's say that we have, in a sense, almost the exact same equation, but here we have x squared y double prime plus xy prime plus, where we had this time the binomial coefficient x squared minus 9, where we have multiplied by y is equal to 0, and rewriting this where I can set up the method of Frobenius. Again, if I divide by x squared, again, we have y double prime plus 1 over x times y prime, and then we have plus x squared minus 9 all over x squared times y is equal to 0. And again, for p of x, again, we have the same numerator, which is going to be 1. Then we have with x squared minus 9, okay, this will represent q of x. And we have setting x to 0. Okay, now we're going to have p naught is equal to p of 0, again, which is equal to 1. And for q naught, you're going to have q of 0, and that's equal to 0 squared minus 9, which will come out to minus 9. So with p naught at 1 and q naught at negative 9, applying the equation that refers to the method of Frobenius, and it's going to turn out that, okay, for the roots, we're going to have positive and negative 3. And again, we're going to select the higher root value, okay, which we had to be at positive 3. So we have in the general solution setup for y, again, have y is equal to x raised to the r of 1 power. In this case, this would be x to the third. And we have times the summation as n goes from 0 to infinity, c of n times x to the n. And again, we have with the product property of exponents, again, x to the third times x to the n, we have x raised to the n plus 3 degree. And now, in setting up what we have, okay, for y, y prime, and y double prime, and we're going to have with the following sets of terms. Okay, for y, again, we have c of n times x to the n plus 3. For y prime, we have the summation of n plus 3 times c of n times x to the n plus 2. And for the second order derivative, again, we have n plus 3 quantity times the quantity of n plus 2 times c of n times x to the n plus 1. And you have the following terms in the expanded form. And again, all of these series run continuously. And taking what we have and referring to what we have in the original equation. And if we look at setting up our terms, and again, I took another shortcut. And you're going to have among the terms, you have 7c1x to the 4th, 16c2x to the 5th from the front. And to the back, we have c0 x to the 5th, c01 x to the 6th plus c2 x to the 7th. And you have the sum of all the terms that come out to 0. And we have is a bit of history that's going to repeat. Again, the lowest degree term will be in reference to what we have with c01, and that was with x to the 4th. And there is no x to the 4th term that exists elsewhere. So c01 is going to go to 0. And from this, we have all the other odd numbers subscripted constants to be set to 0. And as for what we have with the even number coefficients, okay, we have 16c2 plus c0, okay, which will be combined to 0. 40c4 plus c2 is equal to 0. And we have also 72c of 6 plus c of 4 is equal to 0. And now we're going to use as our guide, okay, again, we have for r, okay, the power, okay, that is at 3. And you'll be thinking along the lines of k factorial times k plus 3 quantity factorial once we get into writing what we have as a Bessel function, or of the first kind. Okay, so we have with c of 2, okay, so we have negative c0 over 16. And here, okay, so if we start out with 1 factorial, we have 1 plus 3 is 4 factorial. Now, we have negative 1 to the first in reference to negative c0. You got 1 factorial times 4 factorial. However, 4 factorial is going to be at 24, and 16 is going to be 2/3 of 24. So I have 1 factorial times 4 factorial times 2/3, and I want to keep the 2 at the bottom. And think of dividing by 2/3 as multiplying by 3/2. So I'm going to have in the rewrite, we have negative 1 to the first times 3c0 all over 1 factorial, 4 factorial times 2 to the first. Now for c of 4, this is going to be equal to negative C of 2 over 40, and in terms of C naught, so I have C naught over 640, and we have negative 1 squared C naught. Now we have 2 factorial times 5 factorial. Now 5 factorial is going to be at 120, and we have for 2 factorial that is going to be at 2. Now 2 times 120 is going to be 240, and taking into 640, I have 8/3. Again, so we had that denominator 3 again, so I'm going to put the 3 at the top, and for 8, this will be 2 cubed. So C of 4, we have negative 1 quantity squared, and again we have times 3 C naught, and we have all over 2 factorial, 5 factorial times 2 to the third. And following what we have with C of 6, it's going to turn out we have another fraction, this time with 32/3. Again, flipping 3 at the top, and 32 as 2 to the fifth. We have C of 6 in terms of C naught, and we have negative 1 cubed times 3C naught, and we have all over 3 factorial, 6 factorial, and 2 to the fifth. So for what we have in terms of C of n, now C of n we have equal to negative 1 raised to the n over 2 degree, and we have times 3C naught, and we have all over where we have in the denominator, we have n over 2 factorial times the quantity of n over 2 plus 3 factorial, and then we have 2 to the n minus 1. And if we rewrite, get rid of the fractions and write n in terms of 2k, we're going to have C of 2k equal to negative 1 to the k times 3C naught, and we have all over k factorial times k plus 3 factorial, and we have times 2 raised to the 2k minus 1. And setting up what we have for y. Okay, so again we had the general expression. We had that y was equal to the summation as n goes from 0 to infinity. And we have a C of n times x to the n plus 3. And with n equal to 2k, we're going to have the summation rewritten where we have as k goes from 0 to infinity. And we have of the summation of C of 2k times x to the 2k plus 3. And filling in, now we can move the 3C naught out to the front, and everything inside the summation symbol for what we have in reference to C of 2k, so we have minus 1 to the k factorial, k plus 3 factorial, and we have times x to the 2k plus 3. And notice we don't have a match between the powers to which x and 2 are raised, but we're going to make this quick adjustment. So for what we have in the denominator, okay, we have 1 over 2 to the 2k minus 1, and if I rewrite in terms of 2 to the 2k plus 3, we have 1 over 2 to the 2k plus 3 minus 4, and extracting, so we have 1 over 2 raised to the 2k plus 3 times 1 over 2 to the negative 4, and just bunching together, we have 3c naught over 2 to the negative 4. If I clean this up, so I can just set this equal to 1, we have that 3c naught is equal to 2 to the negative 4, and 2 to the negative 4 is 1/16. So we have c naught is equal to 1/48. So if you just think of it like this, you got 3 times 1/48 is going to be 1/16, and divide by 1/16, so that will go to 1, which I'm going to highlight in blue. And we have, so we have in the formation, okay, we have the summation as k goes from 0 to infinity, and we have negative 1 to the k all over k factorial, and we have times the factorial of k plus 3, and again we have in condensing, now we have x over 2, and we have to the 2k plus 3 degree, and this will turn out to be a Bessel function of the first kind where the degree is going to be at 3. So again, so what we have in the final result, this will be a Bessel function whereupon we have p equal to 3.